if anyone has them. You can also do it online as well. So whatever you like. Today's speaker, Dr. John Guslander, is a perfect person to talk about chemistry of rocks. John has a PhD in chemistry and has played around in the sedimentary rocks in the Gros Ventre as much as any, or more than anyone I know. So another good talk from John. Thanks, John.
Thank you for coming. So I've been hiking around in the Gros Ventre a lot, like Mike said, and what I was hoping is that chemistry could explain some of what I was seeing. I'd heard, like many of you have probably heard, that red rocks means iron, but there's a lot more to it. Is it just because there's iron there, or is it something about that particular iron? And what I'm going to show you is there's iron everywhere, and every rock basically has some iron. A perfectly shaped quartz crystal probably has quite a bit of iron. And what is the origin of the iron? Where did it come from? And then how does the iron in solution as a chemical, the way a chemist would think about it, become a mineral or rock, the way a geologist would think about it. And then we're going to do briefly chert and phosphate, because it turns out iron is involved in the production of the chert and phosphate sediment layers. They're related. And then I'm going to do a couple of brief slides that show how iron is applied to origin of life research. So that previous slide was the Red Hills, and this is the top of the Red Hills, where the Chugwater formation is turning into the, I can't remember the name of the sandstone right above it. Mike, what's that? Nugget sandstone. It's the transition between the Triassic and Jurassic in time. But right at the top of the Chugwater, so the end of the Triassic, it's a very interesting place. So you have green, white, purple, reds, more white. So this is nugget sandstone right here. This white layer looks identical to this except for color. So what most people would call this as bleached. So this is a layer of this sandstone. This purple layer is clay, in the sense of clay being a very small particle. Clay has two definitions in geology, but the one most people think about, and I used to think about, was it's just very small. So here's a purple clay. This green is kind of a clay. Here's more sandstone. I'd like to know what the, what was going on that made this, but I don't. I still don't know that. But I've learned something about the colors. What was happening at the end of the Jurassic was the Atlantic Ocean was opening up. So a big change in the world. Right, so our rock's red because they have a lot of iron. So this is a fact sheet published by the USGS. The most common elements in the Earth's crust. And the reason it's graphed this way is they go by atomic number. So there's hydrogen, lithium, carbon. Right, so the most common element in the Earth's crust is oxygen, by far. So all the rocks that we're walking on, the most common constituent in there is oxygen. By a long ways. It's so common that people don't measure it and they don't name rocks that it's just everywhere. So second is silicate, aluminum. Okay, and these are the most common ones. And here's iron right here. It's number 7 or 8, depending on how you. So it's the 8th most common element in the Earth's crust.
The axis there.
It's a logarithmic scale. So if you go from here to here, the amounts increase by 10. So like a common one, here, manganese and iron often occur together, and there's usually 100 times as much iron as manganese. So oxygen almost equals all the rest combined. This is probably the most useful thing to know about when walking around on rocks if you're trying to figure out what they are. So if you put these two together, you get quartz, silicon and oxygen. If you put sodium, aluminum, calcium, potassium, and silicon together with oxygen, you get feldspar.
Yeah. The things that aren't on there are just too small to show up.
Yeah,
like
they're
gold.
below the 0 line, like gold, copper. So, like you can see why some people thought it would be advantageous to build electrical systems out of aluminum rather than copper, because there's a lot of aluminum. It just takes energy to get it. Titanium's up here pretty common, but I couldn't find a single instance of like this is a titanium rock. It's just kind of dispersed everywhere, I guess. It's not water soluble, and so just because it's common doesn't mean you're going to be able to see it. Like in a couple other things here you see, like lithium and phosphorus. Sometimes you'll hear people talk about a shortage of those things. And really what a graph like this says is it's just the amount of claimed phosphate mines that somebody owns might be small, but the earth is full of phosphorus. You know, it's number 11. So or lithium, like lithium's in the news lately. Maybe that we don't have lithium, but at least the Earth's crust has a lot of lithium. It might not be claimed by somebody or be mined. Now this is the USGS for the entire Earth's crust, but in the Gros Ventre it looks just like this. From the few samples anyway that I had data for. So there's iron everywhere. So why is it red in some spot and not orange? Okay, this is the Earth's mantle, thing below the crust. And I'm not concerned so much about what's in the mantle, it's the way they recorded what's in there. So if you did water chemistry or anything in a chemistry lab, you would expect it to be recorded like this. There's 5.8% iron. But that's not what geologists do. They measure everything but the oxygen, and then they just arbitrarily add oxygens to get it to electrically balance and report what's there, and then see if it adds up to 100, see if they got everything. But this confused me quite a bit. That's why I'm putting it up there. It might confuse you, because there's no calcium oxide in the Earth's crust. Or at least I have never seen it. There's no sodium oxide. It's an auditing procedure to make sure they're getting things right. If you looked at water chemistry, you'll see like this, which is the kind of thing most of you have seen before. Okay, now something a little more difficult. The color of those red rocks indicates something about the electrical state of the atoms. Right? You might have heard the phrase oxidation reduction. So, oxidation reduction is something that was done around 1800, French Revolution times. That's when that terminology was invented. So they don't know about electrons. They have sophisticated enough scales then that they can measure gases actually. They can weigh a gas. And so they learn about oxygen combining with elements. And so they describe processes that increase the amount of oxygen in a rock or reduce it. So that's where that came from. I'm not sure when the words acid and base were invented, but if you looked on Wikipedia to see what an acid is, they would write something like this. But that's exactly the same as a proton. Right? And protons and electrons are something most of you heard about in elementary school. So oxidation reduction means this electron moves from one place to another, from one atom to another. That's all it means. Acid-base reaction, you have a proton. Right? And I put it this way to emphasize this is an electricity thing. It's an electrical phenomenon. Electricity, when you look at it at a small enough scale, is discrete, or quantum, if you want. It comes in little pieces. All right? light is produced and consumed by charged particles, especially this one. So as you have electrons moving around, it can change how light interacts with it. Right? This you probably didn't get told about in elementary school. I didn't learn this till I went to college. And it took me a while to digest this.
So are you talking about how when electrons change valence states, they're emitting?
No, there's many ways that electrons can
not
make
valence
light.
states when they're changing orbitals.
That's one way. That's just one way. Another way is free electrons, if they change their direction, can radiate light. And then it can be of any frequency, like in the sun. It's not just orbitals. Like I'm going to show an example. And solubility is also an electrical interaction. Okay. There's a lot in this slide, I understand, but this is really the heart of why that's red and green appear. So this is iron plus 2. So 2 electrons have been removed from iron. There's also another ion in there. When you put iron plus 2 in water, it's going to attract hydroxides to it. Like here's a hydroxide. That makes the water have excess hydrogen ions, and so the pH goes down. So if you take pH 7 water and put iron sulfate in it, pH will drop pretty rapidly. 4 through something like that. When the iron's in solution, it's not just floating around by itself. It has this octahedral complex shaped like this, and it'll have waters or OHs around it in an octahedral shape. Does everyone get that? So when the iron's moving through solution, it has this octahedral cage around it. The things can move in and out of that cage fairly easy in water. Not in rocks, but in the water. Now, like one way to think of this, if you're familiar with biochemistry, is very similar things to this occur at enzymes. So an enzyme is like a big protein structure that plays the role of these things. It holds the iron in place, or a nickel, and both in industrial chemistry and in biological enzymes, this iron is critical because if you have 2 molecules you want to react and make something, and you just try to crash them into each other, it generally doesn't work very well. You have to get the one molecule to either sit still and then bring the other one into it, or you have to get them both to slow down. It's like making passengers go from one airplane to another. You need an airport so the airplane can land, the passengers get off and wait for the next airplane to come in, all right? So, and that's what this structure does. If an atom can come in here, a molecule land on here, and trade electrons. Iron works very good for that in living things and in industry because it doesn't take much effort to put an electron on or off there. It's like easy to get from the airplane to the terminal, right?
Obviously not a real life example.
So at iron plus 2 in solution is green. If I add sodium hydroxide to this, so I'm increasing the pH, you get a little green precipitate, get some more OHs on here instead of water molecules. If you continue to increase this at about pH 6 or 7, it will turn this color. And that's red iron, which is Fe plus 3. Right? So it's lost an electron. It takes oxygen to do that, and it also takes these OHs hooked on there.
I'm going to ask you a very dumb question.
Go for it.
If you lost 3 electrons, why don't they say Fe minus 3?
Well, Fe minus 3 would tell me that it has 3 extra
Yeah, I know,
electrons.
but why?
I don't know.
Reverse to what you would think.
Well, here's the way to think of it. Defining minus and plus charges is arbitrary. You know, which one you call minus, which one you call plus is arbitrary. So, but once you define it, then this has to be a +3, because if you were to look at its total charge, that nucleus is +3. It's got the opposite charge of an electron.
Right, because the electrons have negative charges, so when you take them away, you create positive ion, and that either 2 or 3.
Talking about the result, not the.
One thing I should say is there's 40 slides here, so there's plenty of time for people to ask questions. So if you have a question.
Is this where we see the relativity profile?
Yes. I think what's surprising is what's true about this one little octahedron will carry through when it makes big rocks. One of the things that chemistry has as a feature that it didn't have to have is when you put an atom in a molecule, it still retains a lot of its properties. Like if you make a hydrocarbon out of carbon, all the hydrocarbons are similar. And they wouldn't have to be that way. You can imagine a world where it's not like that.
In water, there's pH, but is there an equivalent thing in rocks?
No, rocks don't have a pH. Is just something for water. You can describe a rock as saying it would neutralize an acid or neutralize a base. You know, if you put a water solution on it, like what geologists say about limestone is it's alkaline.
Yeah.
And you know, reactive. A chemist would say it buffers it. Well, a chemist would say limestone buffers the water, keeps it from becoming acidic. And a geologist, they say it has alkaline. It makes the water alkaline.
So John, the green rocks that would also seem to grow on, were they formed in anoxic?
I'm going to get to that.
Oh, okay.
I've got 2 questions. When you added this NaOH to the solution and changed it, after the precipitate comes out, is the NaOH still there, or has it decoupled?
When you put sodium OH in water, it splits apart into a sodium ion and an OH minus. The sodium is still in solution, but the OH is hooking up to it.
It's hooking up onto there, okay. And then the insoluble precipitate that happens, is its form still the octahedron?
I'm going to get to that. There is octahedrons, but we're going to really get into the.
What's the pH of the water after this stuff precipitates out?
It's still 8 or whatever I made it by adding this stuff.
And are you going to talk about why, when the iron gets oxidized, that the color transition happens?
I'm going to briefly describe it, but I don't want to. It's very interesting, but it's not something to do on one slide.
He's getting ready to go to a rock show. He wants to be more informed.
So the Fe+3 compound, and I'll get to what that actual compound is, precipitates coating the rocks. And so it looks like this. Here's an example. They would call it, the geologists call this a shale, but it has a coating of in this case, hematite, right? And it's pretty soft. You can break it.
Is the hematite black?
No, it's red.
It's red, okay.
Well, a big mass of it might
Yeah,
be black, but
yeah.
like a scratch test would be red.
Right. Yeah. Most of that's dehydrated. That's why it comes
Yeah,
like that.
I'll get to that. So if you add 30% HCl to that rock for a day, takes a long time, then it'll turn into this. It'll dissolve the iron. This has a yellow tint from iron chloride. It's not really a yellow look. It'd be white if I knew how to do that. So over here, so that should make you wonder, how do you get a stream like that? And what has happened, and bacteria play a role in this, is not knowing, but I would guess the pH of this stream is roughly 0 or maybe even negative. Because that's what it takes to dissolve that hematite off that rock. which it's a problem. One of the things that people tried to do with this in one case was they took a dump truck full of limestone, ground it up and dumped in here to try to neutralize it. And what happened, it didn't work. What happened is right at the surface of every piece of limestone, the pH went up like it was supposed to. And then a bunch of hematite precipitated onto the limestone, covering it. And so then it was no longer effective. And so generally what people have to do to treat like this it's usually mine runoff, but there's other examples, is they have to treat that whole water system as a whole and do some very expensive management of the whole thing. Like, do they want more water going into the stream, less water going into the mine, and how do you do all that? Like a giant example is Butte. They have a giant pit. They have flow from the mountains. They don't want that pit overflowing into Silverbow Creek and going to the Clark Fork. And what they've done is a massive project to control water flow into the pit. And so far it's working.
So how do you get a pH less than 0?
Well, you have more than 1 mole of acid per liter of water. A liter of water is roughly 50 moles of water, so it's easy. It's just the scale that makes it sound dramatic. If you have 10 moles of HCl per liter of water, then you have a pH of -1. So that's like 300 grams of HCl in a liter of water. That's why pH meter is useless when you're working with strong acids like this. Yeah?
I'm trying to interpret this. I hope I'm listening carefully for the whats and wheres in terms of pH in our soils and how basic they are and how most of us who have lawns put ironite on them.
I'm going to get to that.
And I'm having an issue with that with my trees.
I'm actually going to use that.
Okay.
I worked on a farm for a long time, so I've thought about that. And I don't think of soils having a pH. I think of if you rinse some water through a soil and collect it, what would the pH of that water be? Okay, so we talked about it being red. Why are there green spots here? This is the base of the Chugwater in the Gros Ventre.
Is that still Red Hills?
This is by just before you get to the slide turn off. It's at the base of the Chugwater. In the Red Hills, there's this big fault and it's kind of covered the base. This is the Sundance Sea, Jurassic period, and this is green. It's green iron. It formed in a low oxygen environment at the bottom of the water. So it was probably never red. So like the question is, if you see green rocks, was it red rocks that turned green or was it always green? Or I guess you could ask if you see red ones, what's the history? It's not always easy. Okay, besides low oxygen, it could also be a hydrocarbon oxidized the red rock. Reduced it back to iron +2. So a carbon plus iron +3 goes to carbon +4 and an iron +2. Okay, and here's some hydrocarbons: oil, coal, methane gas. And when you reduce the when you reduce the iron and oxidize the carbon, you can make limestone or carbon dioxide. Those are oxidized. So reduced carbon has hydrogens hooked to it, not oxygen. Oxidized carbon has carbon attached to it, makes a carbonate.
You say west of the Mississippi. What happens on the east of the Mississippi?
I'm going to get to that. Okay. So, so this is like a saying, I guess, in farming. It's if east of the Mississippi, you have a lot of rain, and you also have deep soils full of carbon. And so, because of all that rain, there's no carbonate left in it. There's a lot of carbon, though. And so they, as the water goes through there, the things in the soil are acidic. They'll have things like phenols or alcohols, which are acidic, slightly acidic. So if water drained from there might be pH 6. Water from something like peat moss would be pH 5. And so they might add limestone to their soil if they determined that they would prefer to have the pH at 7. And they might also put tiling in their whole field to drain it, which you can imagine very expensive. Okay, in the West, and by West I don't mean Iowa, I mean like Wyoming, Montana. There's still carbonate in the soil because it doesn't rain. And so if the pH there, like the pH of most water that I've tested anyway, was greater than 7. It might be 7 to 8 in the West.
Does it help explain why the crops on the east side of the United States are different than the crops on the west side?
I don't think it explains that. It explains what farmers are doing to add things to the soil. What determines the crops is the growing season and the rainfall. You can't grow corn where it's cold. It has to be, you have to have a growing season of like 120 days for corn, where in Montana you have a growing season of 90 days.
But the pH value has no impact on
it? It has an impact, and that's why they might add limestone, but it's not the key thing that would decide. In other words, they would go, I'm going to grow corn. What do I need to add to this soil to make corn? Like carbon or limestone's not even the first thing. They're going to be adding mountains of phosphorus and nitrogen and all that.
If you put a lot of water on our soils, does that change this whole process if you're watering as opposed to waiting for rainfall?
I don't think you can put enough on to change it that much. But if you had a beaker full of soil, you could put enough water on over time, maybe to rinse all the carbonate out. But what I've seen people talk about, I haven't actually seen it happen, is sometimes people will hope that applying water to a field will wash sodium out. But generally, I've seen the reverse process. They get too much water, the groundwater level goes up and brings sodium up with it. But sodium's more the issue than what the pH is.
But if you're trying to grow hay on the eastern part of the states, you add limestone because the pH is too low and you have to get it into higher than 7.
Somebody was raising hay in Ohio.
I grew up on a farm in Pennsylvania. I did a lot of liming.
Yeah.
40-pound bags of lime
Yeah.
through a lot of fields.
Limestone's cheap. That's why you
Yep.
can afford to do it.
That's
And there's a lot of limestone back east in Ohio and Pennsylvania.
Yep.
Pennsylvania and Mississippi in formation. So one idea I want to get across is to just think of the flow of electrons. That's what oxidation reduction is, all right? It's just an electron flowing from one place to the other. But it's, of course, critical to what's going on in nature. If you took this one step further, and instead of making this green +2, you took it all the way to iron, then you have a smelter. If you put coke in here, is what they would call their carbon. So you take coke and an iron ore like the magnetite, and then you get iron over here, or steel if you really control the chemistry precisely. Most of the carbon on the surface of the Earth is oxidized. It's in limestone. Much smaller part is in this form. So, you can imagine, is there some kind of geologic process that might alter that balance? Take a bunch of this and turn it into methane. And it would alter things. Okay. Let's talk a little bit about the forms that the iron's taking. So, when that iron precipitated, when the pH increased and it precipitated kind of a red-orange in the test tube, it's making limonite first. It has kind of a yellowish brown color here. These are nice samples. If it gets a little drier and it's exposed to oxygen, it eventually makes hematite. So Here, this is, I think, a tropical island where they get bauxite to make aluminum. And so they get a lot of rain. It washes everything away, including the quartz. So there's nothing left but iron and aluminum oxides. The hematite's at the top, where it's exposed to air, but down here there's limonite. And limonite's actually a bunch of different minerals, which I'll show you. This is a banded iron, not a very untypical banded iron. It has some hematite and limonite in it. Most of the banded irons that I've seen are magnetite, like Chuck was showing last night. And so they're not as interesting in colors.
John, what are the yellows in the banded iron?
That's the limonite. Maybe there's something special about this one. You know, if you did a detailed chemical analysis, I don't know. It looks pretty. Here's an example. As you go east from Du Bois, you're just getting onto the reservation here. It's roughly right at the border. This is the top of the Chugwater. Here's the nugget. And here it looks kind of like limonite. So it looks like this stuff. One person mentioned he thought it might be a lake bed at one time. But most of the lake beds that I've seen here where people said that's a lake bed, it wasn't limonite, it was more like green, some other colors. So that's just what the claim was.
Who made that claim, Joe?
I don't remember. It's just, this was interesting to me because this same layer doesn't look yellow like this in Gros. It's the exact same layer, but it changes from that sort of bands of red and purple. Over here, it's this yellow, and there's also something else in here called a nalcine. Little white, and if you dissolve a bunch of the yellow off of there, you see little white spheres, like less than a millimeter, of what I think are nalcine, which is a sodium silicate, maybe from volcanic glass. That's the one thing I got an argument with John Guslander over. Okay. So limonite is actually a combination of these three different things. These are called polymorphs. So if you take that, take these octahedrons, and you can combine them in different ways. You could make octahedrons connect by edges, by points, or by faces. Do you see that? So if you brought two of them together, there's a lot of different ways they can connect. So here's some of the structures that show up. So a lot of variety. These are all different things that could be in the limonite. Here's the X-ray diffraction data, and so it's showing where you get a peak as you move your detector. And so they can identify them based on this X-ray diffraction. The thing that I got from this was when you take a chemical and you make a rock crystal, there's actually an intermediate stage in that, where there's another layer of symmetry and a way of describing things. So there's the molecule here and a mineral here. But in between, there's also this interesting structure, that octahedron. And how you get from that octahedron to that mineral can happen in different ways. You can have these different combinations. And one of the ways, maybe the most important way they figured that out, is using a synchrotron. I didn't know what these were for until this. I've heard of them, of course. You know, they're big science. Cost a lot of money. But what do they do, actually? Like, this is the one in Grenoble. It's giant. It's really a particle accelerator for a different purpose. Instead of colliding things, they're generating X-rays or other kind of radiation. So the electrons are going around in a circle, and the name synchrotron comes from it. It's actually kind of complicated to keep them in that little pipe. They have to synchronize everything, the changes in electrical and magnetic fields. So you have a bunch of electrons going around very fast, and they hit something like this, where there's oscillating magnetic fields. So then the electron, it's called a wiggler. There's actually a couple of other names, but it makes the electron wiggle, which makes it radiate electricity, or radiate light. Remember, light comes from charged particles. Because it's a free electron going in a circle like this, they can generate any frequency they want. And if they adjust the spacing between these, you can adjust the wavelength. And getting an intense X-ray source that you can adjust the wavelength is a big deal. I don't know how you would do that in a lab, a small lab. You know, how do you focus X-rays? How do you generate X-rays of different wavelengths? You know, like the X-ray machine is just one wavelength from a particular kind of event. So these things are a big deal because at very intense source, they can change the wavelength so they can do X-ray spectroscopy on rocks. So people with rocks are big users of this. Biologists are the other users. And also maybe solid-state physicists trying to make make their various products that they're going to commercialize. Okay, so these are some of the things that people find from that synchrotron. So here's hematite, a bunch of those octahedrons, and the way I think of hematite is two of those octahedrons come together to make a dimer by sharing a face, and then the dimers hook to each other. Inside the hematite's not magnetic if there's no magnetic field when the crystals form. And you can think of the spin or the magnet inside this octahedron cancels that one. So the whole mineral structure, each dimer cancels, so the fields are going this way. If you impose a magnetic field from the outside while it's crystallizing, you can get a slight excess of population of one over the other. But normally, or not normally, in the absence of a field, it would not be magnetic. So what I'm trying to show in this slide is how decreasing oxygen affects the iron minerals and sulfur. But iron's what I'm really interested in. Here's oxidized sulfur, which you often see with the hematite, and you do in the Gros Ventre. They both need oxygen. When the oxygen's at its lowest, iron +2 and sulfide, no oxygen, so you get pyrite. Pyrite's unstable at the surface of the Earth. It'll be oxidized back in that direction. And this is, you can actually see this, I guess, in some of the older museum pieces from that were collected in the 1800s. They're starting to corrode. So, a little bit lower in oxygen, like a few feet lower in that island, tropical island, you have the limonite chemicals. This one's goethite. And I should say these are all from X-ray diffraction data. These aren't things somebody made up. This is data from the X-ray diffraction put into this program, which I'll show you. Okay, so decreasing oxygen, you get the limonite. If you decrease the oxygen further, then you start getting a mixture of Fe+2 and Fe+3 in two ways. You can get magnetite, or you can get this clay. This is glauconite. And sometimes people call it this name. I wanted to put these structures out to show you that, clay seems like, it's mud pie or whatever. But if you looked at it in a small scale, it's a very ordered structure, kind of an interesting one. In magnetite, you have octahedrons and tetrahedrons, right? And this is why magnetite can be magnetic on its own. It doesn't need an imposed field, because there's an iron with certain spins in here and different iron here and here, and they don't cancel out because they have different geometries. This one has a +3 in it, +2, and a +3. So it will have a magnetization by crystallizing without any external influence. In this clay, this is the iron octahedrons. Here is the magnesium and other things. Here's the silicate layer. And this
So
is
the X-ray diffraction is how you determine the compound and the shape of the crystal?
the shape.
The shape.
The identity of the elements you can get more easily. So this green stuff right here that I think is glauconite. I got expert opinion from Chuck. There's only a few things it could be, but that was the most likely. So if you see magnetite or glauconite, like this is at South Pass, and this you can see by where the highway crosses the river going to Riverton. This indicates it was formed in a low oxygen environment. Not zero oxygen, but low. So South Pass, when South Pass was forming, there probably was not 20% oxygen in the atmosphere. It was probably much lower. You know, it was 1%. This would indicate no oxygen. So when you see these things, right away it tells you something about the oxygen level. So you can't, like hematite, there is no hematite until after oxygen-producing bacteria exist. So that's one of the ways you can tell when that happened, is by looking for this oxidized iron. Yeah?
It's a simple question. What is magnetism?
Well, it's not a simple
I
question.
know.
Okay, magnetism is what you'd call a non-classical thing. It originates from the spin of electrons, and spin is not from the spin of an electron. It's a property of electrons that that the structure of space is not what we think it is. Like, if you draw a circle in space, everybody here would think you could shrink that circle to a point, right? That's a simply connected space. A non-simply connected space, if you draw a circle, it won't shrink to a point. Like on a donut, you can draw circles that don't shrink to a point. Well, spin is an experimental evidence that space is like that donut. Or a better example would be a Moebius strip. That's why when you take chemistry class, nobody tells you what spin is, because it's just, you hear something like what I just said, nobody likes that.
The answer is spin.
Yeah, the answer is spin.
Spin and
But is it a different spin than, are there different types of spin? And that?
Yes, there's not different types of it, but they have different magnitudes. So all electrons and protons have spin 1/2. Photon has spin 1.
Photon of what?
Light.
Because I've heard photon used for any electromagnetic.
Yeah,
Photon,
well, any
photon.
light. I'm using light in the sense to refer to any frequency. Like there's X-ray light, infrared light. Okay. Since we're on this subject, I'll give one little side story. In the 1920s, a person got a physics PhD and needed a job. His first job was to figure out the crystal structure of these things. Somebody had an X-ray diffraction lab, and he came in there and he was going to calculate the structures. His name was Wigner. And so which he did successful. Well, then he took this thing he was using called group theory, and applied it to space and to special relativity, and got a Nobel Prize and a job at Princeton. That was back in the 30s he did that. Okay. This slide is a warning to me that There's lots of other things out there besides iron, especially aluminum. Remember, aluminum was, number 3 or 4. Aluminum typically is +3, so it can substitute for iron 3. So like in geology, it's like doing a chemistry experiment where you can't separate things. Everything's there. Everything's happening with each other. So you have aluminum, titanium, manganese, all kind of swirling around out there, right? And what was interesting to me as the aluminum increases in this hematite crystal changes from these raw octahedrons to these flakes here. So I guess this is to counteract those pretty pictures that I showed before, the crystals. That if you could see down in those rocks, it might be a lot messier than that. Aluminum's not visible like iron, but it's at least as common. It's everywhere out there, like in feldspars, full of aluminum. The thing that makes aluminum expensive is adding electrons to make a metal. That's why it costs money. But it's actually very plentiful. Okay, remember there was a purple color at the top of that bed of the Chugwater. So why is it purple? And there I came across 2 possibilities. So I was first thinking it could be manganese, because manganese has some purple compounds that I saw in the lab. I didn't know that was relevant to geology. But the problem was when I looked at the chemical analysis, and there's actually some analysis from the Gros Ventre, it's 1% of what the iron is. It's very small percentages. And also, why would it be in one layer but not anywhere else? So I don't think it is manganese in the Gros Ventre. But there isn't a bunch of examples in Utah where there is manganese. This is in Capitol Reef. These marks here have been analyzed. They're manganese oxide. This is Grant Wash, one you can walk through when you're in Capitol Reef. Marjorie Chan, professor at the University of Utah, explains it this way, that you can have water that has soluble forms of manganese and iron, but no oxygen. And so flowing up, in this case, the up part's not critical, but it's flowing in one direction. In the other direction, you have water with oxygen, and so they meet, all right? As the oxygen meets this water with the iron and manganese, the first thing it oxidizes is the iron, because it's more difficult to oxidize the manganese. So it does a separation. It separates out the iron, then the water goes a little higher, and then the manganese starts to get oxidized. So in special circumstances where you have something like this, you get the manganese to separate out, concentrate, and form this. There's also iron in here, but the manganese has been concentrated.
That's frequently called dendrite, manganese.
I'm going to show one.
Okay.
This is a manganese dendrite right by the slide. The slide's kind of interesting in that it's taken this big rock layer and ground it up and shoved it uphill so you can see kind of the inside of a rock layer. Where normally you're seeing these exposed, weathered surfaces. If you go down to the bottom of the Gros Ventre and walk through those boulders, you're seeing a lot of fresh surfaces of the core of a sedimentary layer. And it's a lot more interesting. You can see the heart of the thing much easier. And there's lots of stuff in it. Okay, here's the alternative that I favor. Larger particle size makes the iron oxide up here purple. And there was 2 groups saying this. This is the geologists, and this is the pigment people, which they gave the same. And to people working with pigments, this is the same as an iron oxide or hydroxide, ochre. So they have yellow, red, purple ochre. This gives more technical explanation. So what these people did is they made crystals of hematite, and they made them different sizes. They were able to sort them somehow with their instrument. And bigger crystals, or not, I shouldn't say bigger crystals, bigger structures of the crystal. It wasn't like one single crystal being big. It's bigger.
Total formation.
Yeah, I'm not sure. There's a word on that. But anyway, the structure was bigger. They would be purple. And when they put them in a mortar and pestle and ground it down, it would turn red. Right? So something with the size of that crystal structure would make it purple. I don't understand why that's the case. But they did it experimentally and saw it.
May have to do with just the interaction of light with the crystal itself.
Yeah, but I don't understand what
why?
exactly it is.
Is that surface oxidation?
What's that?
Surface oxidation?
No, because they're just making the crystals. It's already oxidized. It's hematite. It's oxidized as much as it can. They make them big. They're purple. They grind them in the mortar and pestle, and they're red. Okay, that's in the laboratory, which, of course, in geology, everything's different in the laboratory. If when they went out and looked at things like this, it didn't work. If you grind it up with a mortar and pestle, it doesn't go away. But the reason probably is this. They were using pure hematite when they did the experiment. This is not pure hematite, it's a clay. So it's a minimum of hematite or clay. There's all kinds of stuff. In their mortar and pestle, it just didn't work. But that's my opinion. I don't understand why a bigger cluster of crystals makes something purple-like. How the light's scattering in there that would change the wavelength. I don't get that. But there was more than one person did this. This one's the one that they gave the most experimental explanation. But other people in the field have been using that idea. What I can't say is, well, why is there this perfect flat green layer, then a perfect flat red, there's white, very sharp lines, and then purple? I don't know the story there.
Porosity.
Do you know whether they had taken any of those larger samples and sliced them to different thicknesses to see what color they showed, to see whether there was a development of the frequency of the light changing depending upon the thickness?
The hematite crystals are so small you can't slice them. I mean, they're measured in nanometers, say 100 nanometers across.
Well, I'm thinking about 1/8 of an inch thick slice versus 1/4 of an inch or an inch, and whether there is a difference in the light structure due to that.
I don't know that. I don't know.
I just wondered whether they ever tried that.
Yeah. There was probably some people laughing at them for doing research for that. Why is the rock purple? But, I should say there's a tremendous number of people are actually employed using this information, like in wastewater treatment, sewage treatment, water supply. It actually is useful. Okay, where's the iron come from? When I was first thinking of this, I thought, oh, this is going to tell me what kind of mountain range was next to, next to this area. So, minerals that you might find in an igneous rock, like olivine, amphibole, pyroxene, feldspar, when they react with water that has dissolved carbon dioxide or oxygen, they'll form clay and release iron. So here's a quartz crystal, and here's a feldspar. So the quartz is much more durable than the feldspar. So 400 microns, 0.5 millimeter. So it's still fairly large in the sense that you don't see the structure of the quartz. It still looks like a big quartz crystal, just like a macroscopic one. And so here's the clay, this layered thing. This school that was doing this, they were marketing this skill to the oil industry because they care about this kind of thing. Like, how far has this progressed? Has the sediment, has all the feldspar in the sediment gone to that, or is it still feldspar? Which affects things like porosity or permeability. Okay. So this, we're looking 3 nanometers. That's incredible. Okay, so here's a pyroxene. So basically we're looking at atoms. This is like the little octahedrons in here. Like a hydrogen atom you can think of as 1/10 of a nanometer wide. So here's the pyroxene. Here's those layers in the clay. And the pyroxene's like a line of those silica tetrahedrons. And this clay, they're forming the sheets. So you have lines turning into sheets. But what was interesting to me about this is it's not like this is dissolving and then that's forming. It's one continuous reaction where these lines are kind of rotate, like every other tetrahedron's kind of rotate to form a clay. And you can imagine this reaction front kind of proceeding this way. So this is the very first time I've ever seen a chemical mechanism. Usually you have to infer what a mechanism is from experimental results. To actually see chemicals reacting at the atomic scale, to me that's amazing.
Do you know what the speed of the process is?
No. So these are octahedrons, tetrahedrons. Same over here in the clay, and I'm going to do a little bit more of this. You have octahedrons, tetrahedrons, and then single ions like potassium.
John, why would it progress? What's the motivation for that line to continue to move?
The pyroxene is stable at higher pressure under the surface of the Earth where there's no oxygen, no carbon dioxide. But as you bring the pyroxene up to the surface of the Earth, there's oxygen, carbon dioxide, and water. And when those make contact, then it's more stable for the silicate to be in the form of a sheet like the clay. So the critical thing is exposing it to the surface of the Earth.
And it wants to go to where it's a more stable state.
Yes. So some things are stable at high pressure, like olivine, are stable in the mantle, but they will quickly corrode at the surface of the Earth. Like one thing would be a density change. Maybe one mineral is more dense than the other. Like pyroxene could be much more dense in clay, so if you add a bunch of pressure, then it's going to go to the more dense mineral. There's lots of other things, but that's one factor. Okay, here's an amphibole turned into clay. This one's only micrometers, unfortunately. So a millionth of a meter. So you can't really see the reaction taking place, but you can see here's the amphibole and the clay. And then I put a kind of schematic of what these minerals look like. So pyroxene, single chains, amphibole is double chain, and the mica or clay group is sheets of these tetrahedra put together.
John, can't you say too that what you just talked about before there with the pyroxene and the smectite being stable and then becoming unstable, that you can reverse the process through metamorphosis?
Yeah, very good point.
That definition of metamorphosis.
Right.
Heat and pressure.
Heat and pressure.
Heat and pressure, yeah. You just reverse the process.
Yeah.
What happens in subduction?
In fact, I don't understand that very well, but I've heard people talk about, they'll refer to metamorphic grade as like things that reverted to amphibole facies or pyroxene as to how much metamorphism it's undergone, how much pressure and heat. This is my little advertisement for VESTA software. That's that software, and it took me a half hour to learn how to use this, download it and use it. You can take data from a X-ray database and make these structures and rotate them and look at them so you can understand what a mineral is. And I also have one image here of a biotite, which is similar to a clay, at 10 angstroms. That's 1 nanometer. So those are atoms. These are either the potassium, potassium. Potassium, I guess, is because it's big, it interacts with the X-rays a lot. I mean, that's incredible. I don't know what it's going to be like in 50 years, but that's what's happening right now. Okay. Clays. Not as pretty a picture, but it's more of a schematic. So you can have different kinds of clays. Some have an octahedral layer of 2 tetrahedrons for each sheet. And then some have just 1 octahedron and 1 tetrahedron sheet. Some people won't call that a clay, they'll just say that's separate. And then what's in between here determines the strength of it. Like mica, you think of very differently than as clay. And mica is held together with a stronger bond. It's not even on here, but so these ions in here, like potassium, sodium, they can kind of move in and out of there. So these are like natural ion exchange resins. So as water's moving through these clays, its water chemistry can change. It could change out of sodium for calcium, like a water softener. The clay, this kind of clay, you find like bimatizzi. It sticks to your car, or at least that's my analysis. I mean, I didn't do a chemical analysis.
Not when it's dry.
If it sticks to the car, you know, it doesn't. You can wash it, and it's still some of it there. It doesn't like to leave. Then I call it bentonite. Okay. The stuff in the Gros Ventre is not like that. I'm calling it illite on that basis. The other basis was the professor at Wyoming said most of the older clay was illite. But, you know. Okay, so how does iron get to that red bed? If a pyroxene in a mountain or an amphibole is corroding and making a clay and releasing iron, how does it get here? Because the problem is, Fe+2, if it's on the surface of the earth, like in a river, and almost everyone I've read thinks that the red bed like the Gros Ventre is ancient river system, maybe lakes, that kind of thing. Fe+2 can't be dissolved in a river and transported because it would be oxidized to Fe+3 and precipitate. So it could be transported as a small suspended silt particle, like you see each spring sometimes in like the Hobax often has red flow, or it can be wind blown. So I think that most people think that the iron in the Chugwater formation was blown in by wind.
No.
I don't know. I don't know how you tell. So why is there a red bed coming off the Wind River Mountains by Du Bois, if we went to visit that one, and off the Sierra Madre by Lake Gasiuk, which we went to visit last summer, but not by Matizzi? There's no red bed there. And there's a lot of iron in the soil by Matizzi. You can find iron balls in that clay layers by Matizzi. So there's lots of iron. My preferred explanation is there's a higher carbon content in that soil. There's more rain, more plant growth, so you get more carbon material in the soil. But it's also a different clay. But you know, the question is, if you explain why the rocks are red in the Gros Ventre, you have this nice explanation. Then you have to also explain why all rocks aren't red. Why are they brown or black over here? Right? So I think that's what's going on. There's probably magnetite or things like that in that soil. I don't know. It'd be interesting to test it.
talking about comparable, the same formation, both places?
No. I'm talking about two formations that both have lots of iron, but one's a red bed and one's black or white. You know, so in the Gros Ventre, the Sierra Madre, Wind Rivers, there's some red beds. But on the east side of the Absarokas, by Mtitsi or Powell, or further up the Gros Ventre, it looks this color.
Europe and the Cretaceous there.
Yeah. But so why is the Cretaceous not a red bed?
Those are marine sediments, and they're probably deposited in a subox, not
Sure,
anoxic, but suboxic.
But I mean, this is being exposed to the air right here. Why isn't it red?
How fast is the reaction?
I was going to say, how long has it been exposed?
Yeah, I think it's been exposed fast enough. But that's what you have to think about. If you have an explanation for why something's a red bed, you have to also explain why these other things aren't red beds, right?
Well, you said it earlier. It has to do with, the extreme is very anoxic to very oxic environments.
Yeah.
And those sediments were deposited in the bottom of a relatively shallow continental sea that was fairly anoxic.
So that's a good point. It's the original history of the rock has a lot to do with it.
And Chugwater, I thought, was sort of tidal flats.
A river, surface river.
It's in a fairly arid environment.
Fluvial, I think is the word.
Right,
it's
arid,
used for that.
but lots of oxygen.
Lots of oxygen, not much carbon or living things, as far as I can tell.
Yeah, it was a real bad time on Earth.
So there's no carbon in Chugwater.
Late Triassic was a bad time.
That's it.
Yes.
It's in other words, something you can get at this is, was there a lot of living things? It doesn't look like there was a lot of living things in the Chugwater. It's a barren place. I'm going to show another barren place in a minute. This, not everybody agrees on how red beds get made, right? This is another person. I'll show more of him later. But he looked at the Eocene White River Formation, so that's 50 million years ago. And it's not a red bed, but he thinks it will become one. He thinks that this limonite here was blown in by the wind. Dust rims is what he calls it. This is a quote from his paper. So he thinks eventually that will be a red bed. Not everyone would agree with that.
Not everyone's going to wait for it either.
Yeah. Okay. This is a desert in Libya. And these are footprints. So it's kind of the start of a red bed. The reason I kind of knew to look at Libya was a geologist who was working there, was exploring the sand dunes. I forget his name right now. He was based in Colorado. But there was pink sand dune fields in one place and white ones in a more distant place. And he followed them back, and the red ones were next to mountains that had metamorphic cores with lots of iron. The white dunes were next to a quartz formation. I should know his name, but I don't. So anyway, I went looking to Libya, looking for photos, and found this one.
So is the surface red, and once you scrape that off?
Yeah.
It's
not red all the way down. Never rains there.
So is that a scrape or is that pressure from a footprint?
It's pressure, it's sinking in. Yeah. Walking along, on the beach.
And will it change back?
I don't know. I assume it will.
Give it an hour or 10 days or?
Yeah. The geologist, it was kind of funny because he said it never rains there, but on geologic time scales, there's plenty of water for reactions, because if it rains once every 100 years, that's a lot of rain after 1,000,000 years.
Actually, this process showed up in the last Star Wars film.
The other thing to keep in mind is a desert like this one, or the Chugwater, it's not the same for millions and millions of years. It goes through cycles where it might have a wet cycle, a dry cycle, because of the change in Earth's orbit. and that's documented in the Sahara. So every roughly 25,000 years, this will go through a wet period. There'll be rivers, and people migrated along those rivers. So, but I know nothing about it except that picture there. That,
How old is that? The footprints?
a couple years.
Not very
That's somebody trying to convince you to go there as a tourist. You just reason. Okay, these are the details of some red beds in Utah. Marjorie Chan looks at that. She's been looking at it for 20 years. She gets a lot of funding from NASA because she's trying to develop programs for analyzing Mars. And so she wants to understand why these patterns exist in the red bed, which I'm not going to get into except to just state the result. After 20 years, I've read a bunch of her papers, and she's kind of gone through this transition from what chemists thought in 1900 to what they're thinking in 1980. So in other words, she's been doing a lot of work. And this is a modern chemistry thing. Lots of chemists wouldn't know what a Turing structure is. It's named after Alan Turing, the famous code breaker, computer person. He wrote one paper trying to describe how nature forms things like living things, like how do embryos go through morphogenesis? What's the mathematical base for that? How does that happen spontaneously? And so I'm just throwing that out there. That's what she's saying this is. And she's getting help from some people at Los Alamos. She thinks the red beds form fairly quickly after a few thousands of years after the beds laid down to be red. So, in other words, in contradiction to that White River formation.
Laid down, exposed to air, or
well, it's a river plain, and so they're laying down and being exposed to air happening at the same time. I'm kind of leaning towards this, but that other guy is way smarter than me as far as geology. I've read a lot of his stuff too. Okay, now I'm going to go on to how iron relates to the phosphate and chert sediment. So here's Crystal Creek, here's the Chugwater red bed, Dinwiddie Formation, and then you have chert and Phosphoria in here. They're close together, and they're related. Here's the close-up of the chert bed. Can you see these features? They look like cylindrical, like this. And so I didn't know what they were originally, but Leif Tapanila came over. He's been over here speaking before a couple of times.
He'll be back this summer.
And anyway, he's come over and helped Mike identify a few things, including his expert opinion is this is sponge metal.
It's what?
A sponge metal.
So they're fossils.
Yeah, they're fossil sponges. Yeah, it's not a living one. Here's easier to access exposure when you're on the Gros Ventre Road, but it's I don't see any sponges in this.
What's the definition of chert?
I'm going to get to that. I'm going to really get into that. Okay, so we're going to talk about the silicates and phosphates, and everything I've seen in nature, these don't change their oxidation state. The phosphorus in the silicon's always in this form, these tetrahedrons. And they don't, if you put these next to carbon or iron, it's not going to oxidize them or reduce them. It's very unreactive. And this one's water soluble, so it's perfect for making structures in biology. You can make a structure with phosphate and hydrocarbon, and the phosphate won't oxidize the carbon. So those phosphates are used to make cell membranes, DNA. Like DNA is a strange polymer in the sense it's water soluble. Most polymers that are made out of hydrocarbons don't dissolve in water, like plastic doesn't dissolve in water. But because it has a phosphate backbone, it's water soluble. Very long chains of DNA are water soluble, which is a good solution.
Define water soluble for that.
If you dissolve DNA in water,
Anything.
it won't clump up on the bottom. Like if you put most hydrocarbons, if you try to stir them in water, you'd find them at the bottom of the beaker in a black mass, especially if you heated it, where DNA would be floating around in the water.
So gravity doesn't affect it.
At room temperature, no, there's enough energy in the water molecules to keep it suspended, yeah.
Will it keep its helical structure, or
Yeah.
you can reconstitute it as?
Right, you can make it fold and unfold in the water. You can do that kind of thing.
But it stays suspended.
Yeah. In fact, suspended, it's not, I use that word, but that's not right. It's dissolved. It's more than suspended. This makes a terrible constituent for something like DNA because it's not water soluble. Sulfate would also be a terrible one because it would oxidize the hydrocarbon. So if you try to make a cell membrane with sulfates at the ends rather than phosphates, eventually it would destroy the cell membrane. It would oxidize the fats. So it's not a coincidence that phosphate's used the way it is. It's just the perfect solution. The phosphates, like our bones have phosphates, our teeth, some shales, like shells, not shales. This brachiopod has a phosphate shell. And of course, living things are full of phosphate in their DNA and all of that. But how it actually becomes a phosphate deposit is complicated, I guess. So I'm just going to give an overview. So if you look at the phosphate beds, they look like this. Mead Peak, remember, is one that you can see by Astoria Bridge. So here's a fossil shell, and here's the little phosphate. This guy calls them a Steinkorn. Why they form, or this is from paper where they're trying to show all these different beds in context. And this is what it looks like around here, except for the limestone and this carbonate shale are both sandstones in our area. But otherwise we have this phosphate and a chert, we have some dolomite and a red bed and evaporites. This describes the Gros Ventre and eastern Idaho. And what he's saying is, in the present time, if you can't get apatite at the surface because there's so many living things that consume all available phosphate. So you're not going to precipitate apatite. Below 200 meters, the ocean has more carbon dioxide dissolved in it. So at high pressure and low temperature, you dissolve more carbon dioxide, which makes the water more acidic. There's no OHs to precipitate apatite. So precipitates in this band where there's less carbon dioxide. It's warmer, the pressure has dropped, so there's not as much carbon dioxide dissolved, and there's less living things, so you get the phosphate deposits. If you could look at this closer, so you have, say, a goethite. Really what I want here is a long chain polymer, like 20, 30 of these octahedrons hooked together. That's what some people speculate is in there. It's kind of sweeping through the water and grabs onto a phosphate or a silicate tetrahedron, kind of like this. Okay? So start sinking to the bottom. It'll cross a line somewhere where the oxygen level starts to deplete. This line might be actually in the sediment at the bottom of the ocean, or it might be halfway down the ocean, or halfway down a lake. There are some volcanic lakes in Sumatra where this line is, say, a couple hundred meters below the surface, so they can measure it very easily and do analysis. So this iron thing grabs onto the phosphate. It's coming down here. There's calcium and OH, makes the apatite. Calcium phosphate with the OH there. But it's anoxic down here. So now this iron can get reduced to a more water-soluble form and go back up. It doesn't make an iron precipitate down here. It just precipitates the apatite. The iron can kind of go in a circle. See? And even this view, where it seems a little complex, is probably really oversimplifying it. The thing that surprised me most was several researchers report seeing right at this line, this organism, single-celled organism that must be living off this electrochemical difference here. But it has these iron phosphate precipitates all around it, and it's living right where the line is. When that line is below the ocean sediment, there's a very diverse population of living things. Maybe it's the most diverse on Earth as far as single-celled organisms. Okay, the chert. So lots of single-celled organisms use silica as their shell instead of calcium carbonate, like radiolarians, diatoms. And when they die, that silicate goes down to the bottom of the ocean and reacts. So opal, which you can't make chert or quartz at the surface of the Earth because it has to be under pressure. You have to have higher temperatures and higher pressures than the surface of the Earth. So the thing that's actually coating an organism is not chert or quartz, it's opal, which is a hydrated silicon dioxide. It's got water. And it forms these little spheres that are about 250 nanometers in diameter, which is roughly the wavelength of visible light, so it can form a diffraction gradient. So when you have opal, it diffracts the light. You get rainbow patterns. This is the X-ray diffraction pattern. And here's the density. So as you increase the pressure, so it's been buried, and it's subsiding. So the pressure's going up, temperature's going up. It will form opal CT. The C and the T stand for two different polymorphs of silicon dioxide. And so you start to see you start to see sharp peaks in the X-ray diffraction. And you get these funny looking balls here where this is 1 micron right here. So it's a little bigger scale than this one. You increase the pressure more and you get quartz, this spectra. And chert is quartz that you can't see the crystals. The crystal size is smaller than micrometer. Cryptocrystalline is the word some people use. It's big enough that they can see it, they can get a good X-ray spectrum. One thing I want you to notice, the density of the opals too, for the chert or quartz is 2.65. If you
How do you measure the density?
well, you can take like a quartz crystal, put it in a graduated cylinder with water and watch the water level increase. That gives you the volume.
Right.
Then weigh the crystal and you get the density. How they do
2
it.
nanometer crystal, I don't know how you do that.
Well, I've done it with the big crystal. I don't know how you do it with the small stuff. Not all opal is those perfect spheres. So here's some other examples. And the biggest reason I put that in there so you could see this. So this is 1 micrometer right here. And here's growth rings in the opal. Now, I don't expect you to get a lot of this, but here's the tetrahedrons in quartz. Mainly what I want to show is quartz is not this space-filling thing where everything's the same. There's patterns inside a quartz crystal of these tetrahedrons. You're used to seeing these complicated crystals of quartz with all the different faces, but inside there's tetrahedrons, really simple ones, but they're combined to make these structures. Like here you can see this kind of distorted hexagon in here. So you can't fill space with a tetrahedron. It's not like, it's just like floor tiles. You know, you can take a square tile and cover your whole floor and they're all touching. There's no empty space. When you combine these tetrahedrons, there's going to be empty spaces in between them. If you use that VESTA program, you can twist these around and look at it and see it a little clearer. So there's probably 100 names for quartz if you looked up on the Wikipedia or something, but I just try to keep two definitions. There's big quartz crystals that I can see that I call quartz. And like sandstone's big enough, it's still a quartz. And there's silicon dioxide where the crystals are too small to see, which I call chert. And some people would add calcandine, which is like a fibrous chert. But almost all the other names are for retail purposes. They're trade names for, you know, amethyst. It's a trade name for a quartz crystal. It's got some impurity that changes the color of it. So just think big crystals is quartz, very tiny crystals is chert.
I was just looking this up about color, you know, you were talking about rosy purple. Amethyst has magnetite in it, and it's almost always purple.
And so like, here's a chert that's red from the Amsden Formation. This is in the debris pile of the Gros Ventre slide. And of course, there's lots of iron around there.
And so it's the six-sided, you know, when you see a quartz point, that's related to the actual structure on the microscope.
Yeah. I didn't put any slides on it because it's very complicated, but it's like two helices winding around each other in opposite directions of these things. It's, there's something called the quartz page, and that's where I recommend going if you want to see that. One of the things that I got out of making this talk was that it is possible to understand minerals. For a long time, I didn't think it was possible to understand them because I looked at the ball and stick photos and I couldn't understand them. You know, what is the structure of these things? It's just a mess. But if you start with these building blocks, the tetrahedrons, the octahedrons, and imagine them putting together, then you can make sense of minerals. It still takes some work, but it's possible. Okay, 3 slides on the application of origin of life. And I'm going to show 3 commercial products. So this is not speculation, the products anyway. These are things people are trying to sell. Okay, so this one, here's that iron oxide layer, a phosphate, and of course they're not using that nice VESTA software, but I think you can still get the idea. There's a phosphate hooked to the iron oxide and a hydrocarbon hooked to the phosphate. It's kind of like a base from a nucleic acid. And here, let's see which one. Here the hydrocarbon is hooked to the iron oxide and the phosphate's hanging off of it. What's interesting about this, if you can imagine this unit here floating around in the water, if you have one of these hooked to the iron oxide, another one comes and lands on there, it can hook to this phosphate and it can make a chain. Okay? Okay, this one's a really complicated one, but again, somebody made this and they're trying to sell it. Okay, so here, it's a little different structure. Here they have the iron core, iron oxide core, then the quartz. So here's the tetrahedra. Then they have phosphate tetrahedra on the outside of those silicate tetrahedra. And they're attaching this very complicated hydrocarbon to those phosphates. So my point is that even though life is complicated, that doesn't mean it can't be, made.
You're not saying this is life.
No, but the way to think about the origin of life is to stop thinking of life as some magical thing with a big gulf between it and non-living things. You have to think of how do you get from here to there slowly, step by step. So a good way to do that is to start with minerals. Think about them.
But you had to have water because you had to have solutions.
Yeah, that's what most people think. Yeah, that's what I think. Like one of the things that's unique about the Earth, it's not just as life, but the temperatures and pressures on the surface of the Earth are rare. Like when I was first learning chemistry, I thought what I was doing was normal. But most of the universe has nothing like the surface of the Earth. It's all these things like the sun where there's no chemistry in the sun. The iron in the sun has all the electrons removed from it. It's completely oxidized. It's all strong force, weak force, all these things that I thought were exotic. But those are the more common things in the universe. The surface of the Earth is a very unique thing chemically. If you get too high temperatures, you can't do anything like this because it all breaks apart. Above about, say, 2,000 Kelvin, you can't have a molecule. Maybe you can have an iron oxide in a dim sun, I don't know. But above around 2,000, below roughly 200 Kelvin, it's too cold to have chemistry. It's just that narrow range here where you have interesting chemistry. The chemicals like rocks seem pretty sturdy to us, but in the bigger scale of the universe, they're fairly weak structures.
Just so you know, we might have to be out of here in 12 minutes.
Okay, I got one more slide. This is a fat hydrocarbon hooked to a magnetite, like a cell membrane. Another way to look at it is this is a soap and this is a dirt particle. And then imagine these inside small cavities, because the critique of those previous things would be, well, you make a polymer, it floats off into the ocean, you never see it again. You have to keep all these chemicals together if you're going to make some kind of living thing. Well, those black smokers on the ocean bottom, or the alkaline smokers made out of iron sulfide, have these little chambers where what could happen. Okay, that's the end. These are 3 people that helped a lot. So Marjorie Chan, she's the expert on red beds. James Drever, he just retired from the University of Wyoming. He's where I learned about clay. And Pierre Poufal, I guess, he works at Queen's University, but he used to be in the US, and he has worked here in Idaho, Jackson area. And then all the X-ray diffraction data came from there. Okay, that's it.
Thank you.
I was looking up something about magnetism in magnetite, and apparently the outer D level, the highest orbital level, there are 4 unpaired electrons, which can have the same spin, which is unusual.
And that's why those transition metals are the color bands, because they have electrons.
And of course, then that could give a local area a net magnetism. But then they're all oriented in different directions. But if you then align them, you can get something that's magnetic. That's interesting. Oh yeah. Next, you mentioned that, but yeah. There's a second follow-on to this one, which will be in September. Yeah. Okay.